So good morning everyone and welcome to this morning's webinar. My name is Alison Starkey and I am the Communications and Marketing Officer at Sugar Research Australia. Today, Seema Yadav from the University of Queensland will be presenting on the topic of improved genomic selection. The webinar will consist of a presentation for around sort of 30 to 45 minutes, followed by a Q&A session for 15 minutes or so. During the presentation, we ask that all microphones are on mute. However, you can type questions via the chat function at any time during the webinar. You can open that by clicking on the little speech bubble icon located on the bar at the top of your screen. Seema will probably come back and answer your questions during the Q&A. If you'd like to ask a question during the Q&A session, you can either type it into the chat again, or you can raise your hand using the hand button, little hand icon that's also located on the bar at the top of your screen. Obviously, if you're called on to ask your question, you'll need to unmute your microphone to ask your question when prompted, and then we ask that you remute your microphone. Upon completion of today's webinar, it will be uploaded to our website if you'd like to come back to review it or to recommend it to anyone else. I'm now going to hand over to Dr. Stephen Mudge, the Program Manager for the Research Funding Unit at SRA, who will introduce Seema to us. Thanks, Stephen.
Thanks, Alison, and thanks, Seema, for offering to do the presentation today. So, as Alison said, Seema is a PhD student at Aussie Institute, working in the Centre for Animal Science with Professor Ben Hayes and Dr. Kai Vosfels. She's part of a larger team working on an SRA-funded project looking to implement genomic selection to accelerate genetic gains in the sugarcane breeding program. Before joining EQ, Seema worked as an international consultant at the Quantitative Genetics Cluster at the International Rice Research Institute in the Philippines. Thanks again, Seema.
Thank you. Thank you, Stephen. I'll just start sharing my screen now. Yeah, is it visible now, my screen?
Yes.
Yeah, is it visible, right?
Yes, it's in presentation mode now. Thanks, Seema.
Thank you, Stephen and Alison, for the introduction. So let me start by conveying my best wishes for 2021 to all of you. And I hope May this year will bring some new opportunity for all of us. And it's really a great pleasure to virtually meet all of you. And at this outset of the new year, I would like to thank SRA and my supervisor committee, Professor Ben Hayes and Dr. Kai Vosfeld, for providing me this opportunity so I can present my work on this platform. So today I'm going to talk about improved genomic prediction of clonal performance in sugarcane by exploiting dominance and epistatic effects. As we all know, the agriculture is now the keystone that driving economic growth in Australia. And if we will talk about the sugarcane, the Australia is the second largest supplier to the raw sugar to the world market. And if we will talk about the worth of sugar production, that's almost at $2 billion economy in Australia each year. And when we will talk about the production trends, if we will look, I'll just start my pointer. And if we will look at all different crops over the past 60 years, there has been increased production. And this blue line is showing here the sugarcane. sugarcane production has been increased almost threefold in the last 60 years. But if we will see the rate of improvement in sugarcane as compared to other major cereal crop is compared to low. And whether we talk about Australia, that's showing the black lines here, or other top sugarcane producing country, there is no substantial gain we can see in the special cane yield in the last 2 decades, or we're saying that the trends are tend to plateauing. The biggest problem is the overgrowing population. The world population is projected to increase 25% over the next 30 years. And the plant production, the global demand for plant production, whether it's terms of food or in the energy, is an all-time high. And if the sugarcane, if we will say the demand for sugar and the products, the byproduct of sugarcane is expected to continue to grow because both of the population growth and most important, the rising income level. So to meet all the demand, so we need to increase the gain at least 2% per annum. But the main question arises here, how can we increase the rate of genetic gain in the sugarcane breeding program? And if we will talk about in a quantitative genetics framework, the phenotype is an expression of genotypes and the environment. So there are two major ways we can increase the gain by improving the management practices, or there are some novel technology, emerging technology like geospatial, artificial intelligence, and precision agriculture. They all are utilized in sugar breeding to improve the management decision. But we don't. The main area we need to improve the sugarcane productivity is the improvement of the genetic material of the modern sugarcane cultivar. But when we will talk about the genetic gain, it is very easy to understand in terms of the breeder equation. This right-hand side, this equation is showing the breeder equation. That this is basically a guide to the breeder. We can quantify all the potential bottlenecks in the existing breeder schemes, and the component of this breeder equation, I represent here the selection intensity, which is a proportion of selected parent in the next selection cycle. And I represent here, if we will go about the phenotypic selection, is the square root of heritability. And this sigma A represent here how much genetic variation exists in the population. And L is a breeding cycle. If you will see left here in the screen, this is a commonly like the most important component in a plant breeding program, where we will start any breeding program with the targeted cross based on the breeding program. And the evaluation of these large number of progeny is done different stages of the selection, and then the individual with the different characteristics are specifically breeding program they are selected. So this the whole three components are going on and continues to going on, and the total time required basically to complete all these steps is called breeding cycle. So for the genetic equation, we can see if we will increase the intensity, heritability of the trait, and if we have a reasonable accessible genetic variation, we can increase the genetic gain, or you say response to selection. And whether we will decrease the breeding cycle length, it will give the same effect, the high genetic gain. And to understand the genetic gain, it's easy to say like genetic gain is basically the improvement in the average genetic value of a trait, and that comes from the selection. But within a population we are talking, and given specific time period, and the time period we're talking about here is the breeding cycle. It's very important. It's virtually, we will again talk about the genetic gain. It's really, if any trait is heritable, it's acceptable. We can go for genetic gain. And if I will show this figure, the black saying the base population, And in the next breeding cycle, if we will say there is a difference in the average genetic merit of a particular trait, what we are interested in. So this is a conventional sugarcane breeding scheme, the SRA, as following. The first step here, of course, we will crossing is done, where is creating a genetic variation in the population, which is going to exploit it in a number of stages of selection. And in the last, the propagation is propagation. So in the whole breeding cycle, I will say in the sugarcane conventional breeding scheme, take almost 7 years of the selection and the 3 years of propagation. So it took almost 10 years to complete one breeding cycle, and it take longer than 10 years to successfully if we release a cultivar. So these conventional breeding scheme, of course, due to long breeding cycle, they are time consuming and as well as the resource consuming. This is a big limitation in the conventional sugarcane breeding. And one of the most important things, the propagation of heterozygous clone is done by the clonal, also vegetatively propagated. So what we will say, the progeny evaluation is capture basically the total genetic variation, which comes like additive plus dominance and the epistatic effect. And if we will select the parents for the next cycle based only on the phenotype, it will always limited by the less selection accuracy. Because most of the complex, or I will say the economic trait we are interested in, they are largely affected by the non-additive genetic effects. So here I'm going to give you some heritability estimate, what we are more interested in sugarcane, like cane yield and the sugar content. So in the past, basically, if I will say that this X square is showing the narrow sense heritability, and most of the trait is showing the less narrow sense heritability. That's also a giving an indication, or it's a measure that traits are mostly affected by the non-additive genetic effect. But in the past study in the sugarcane literature, we also found that researchers have done researchers use already some factorial mating design to quantify the specific combining ability and the general combining ability. What is the general combining ability and specific combining ability? Is if in very simple say, if I will say, the genetic combining ability is just is the breeding value of a parent that is inherited from one parent to an offspring. And the specific combining ability is a relatively, I would say, the performance of a cross where the non-additive genetic effects really important. And this metric, like the ratio of GCA and SCA, is also given indication that how non-additive variance is important for the complex trait, basically cane yield and the sugar content in the sugarcane. So there are like long breeding cycles and the selection method. There are some biological challenges also in the sugarcane breeding program. Like sugarcane is the highest complex genome, is one of the highest complex genome in the plant species. And the genome size is quite big, it's a 10 gigabyte. The high level of polyploidy, that means at one given locus, there are a number of allele, disaggregating allele, that make this clonal breeding is really challenging. Due to outcrossing species, there's a high level of heterozygosity present in the clones. Effective size of the population is very less in the modern cultivars. And all these, but we will also face some practical challenges like poor synchronization of flowering and some time in the genotype environment interaction. So these all challenges the sugarcane breeding make challenge, and it's all limit the what do you say, limit the genetic gain in sugarcane. But we can't like the traditional breeding really did what do you say, that remarkably we have tremendous growth until now is due to the traditional conventional sugarcane breeding. But now is the time we can exploit the genomic information. And it will be, I will say, it's a second boost. So we can increase the sugarcane productivity by exploiting genomic information. Genomic selection is the kind of, we will say, is a breeding tool, and that involves the use of genomic information, where we can test the untested genotype. Basically, this is built on the premise of we are going to use some DNA marker profile, and it creates an association between DNA markers and the phenotype. So we can predict some values of untested genotype based on their genomic marker profile. In this technique, basically we are use simultaneously all the DNA marker. So there are basically two steps when we will implement the genomic selection. It's the kind we have to create a reference population where all the known genotypes and the phenotypes from the field data. So, and based on this reference population, we develop a prediction equation. And based in this prediction equation, we calculate all the marker effects. And by using this prediction equation in the selection candidate, which are not tested in the field, but they have some marker genotype. So based on their marker profile, we can predict the breeding value of the selected, what do you say, the genotypes. And we all know that this strategy is implemented first in the livestock breeding, and they have already livestock breeding has already changed. And most of the cereal crop are successfully implementing genomic selection, but this is a quite relatively new in the sugarcane, and it will give boost to improve the sugarcane productivity. But the genomic selection, if we will see in the terms of the genetic gain equation, breeder equation, what it can do. So the first thing is that we don't need to do the phenotyping at each selection stage. We easily skip some stages. We will just genotyping as early as possible. We have a DNA marker available. We can skip some tests, and it will automatically reduce our breeding cycle. And reduce the breeding cycle because this is inversely proportional, so genetic gain will automatically increase. And with this genetic information, we can improve the accuracy of selection candidates. So if we will say if this R increase, the genetic gain will increase. Because of the early testing, where I will say the selection also accuracy increase, because in the early stages of selection, there is a very less replication and the genotype is tested in very low environment. So accuracy will increase, but if we will use the DNA information. And if we will screening, we can screen large number of genotype. We don't need to test in the field. So we can increase in the selection intensity also if we will genotype and predict large number of genotypes. So basically in the breeder equation, if we will see the three components, the selection intensity, accuracy, and breeding cycle, automatically we can fit in the genetic gain equation. If we have some existing genetic variation exists in the population. But the genomic selection is depends upon some different factors. So prediction accuracy, it's basically first the heritability of the trait. High heritability trait will we can get the higher accuracy. The training population size should be enough big so we can estimate all the marker effects. The relationship between training and the prediction population. We should have some good phenotypic data, and the genetic platform and the marker density is also there some factor which affect our genomic prediction accuracy. But the most important thing I will say is also genetic architecture of the trait, whether the trait is affected by only additive effects or the non-additive effects. So goal of this project is to basically implement genomic selection in Australia sugarcane breeding program, where we are more focusing on the complex economic trait like ton can per hectare, commercial cane sugar, and the fiber content. And the TCH and the CCS here is a low heritability trait. And I will say that TCH is the most low heritability trait. And the best part of the genomic selection is it can be a use for the low heritability traits. So again, for implementing genomic selection or for using genomic prediction, we need to create a reference population. So in this regard, we already 4,000 clones are genotypes by using the F matrix exome SNP array. And the phenotypic data comes from the final assessment trial from 2013 to 2017. Year series clone from the 4 regions of the Queensland. So most of we have a big reference population size. So genomic selection also what we can use the different strategy we can apply in the genomic selection. So first we can estimate the breeding value of a parent basically, which is going to be entered in the next selection cycle. And breeding value means that additive effect that's only directly passed from the parents to their offspring. And we can also estimate the clonal, the variety performance, because the variety, because due to the clonal propagation, the non-additive effects are associated with some additive and the non-additive genetic effect. And the non-additive genetic effect, they cannot be inherited consistently. It depends upon the specific genotypes. So in regard of this, some initial results, the Professor Ben Hales and Coy Fosful, they just did some initial additive GBLUF model by using some different genomic prediction model, which are easily we can set up in the sugarcane breeding program. And by using these additive models, we can easily see we have a promising genomic prediction. So we can easily apply in our new complex product. If you will see here, the fiber is basically a high heritable trait, and we have a prediction accuracy is a much higher than the CCS and the TCH. TCH is the lower heritability trait, as we will say the prediction accuracy depends upon the heritability of the trait. So low heritability, we always expect the low prediction accuracy. So my objective for this study, we have to partition the genetic variants, basically additive and the non-additive genetic effect. So by extending some GBLUF model, because we have now SNP, we high density marker, which make it feasible. So we can incorporate some non-additive genetic effects into the genetic prediction model by exactly the same as a BLUF methodology we use it. So basically, genomic prediction model, I will again explain the phenotype is a combination of genotypes and environment, but the total genotypic value is additive and non-additive effect, which is normally considered by dominant and the epistatic genetic effect. So first, we always say conventional genomic selection model. In my study, I used the additive model, the GBLUF. The GBLUF model basically used the genetic relationship among the clone to predict some untested phenotype. And in each step after that, I incorporate non-additive genetic effect and the heterozygosity in additive model. So I will say this is a standard GBLUF. At each step, I included, first I included dominance in my model and then epistatic effects. And each tree model is extended by using heterozygosity, because sugarcane has a more heterozygous clone, and we set heterozygosity as a fixed effect, as a covariate in our prediction model. And then because both these approaches, that GBLUPs is a linear approach, but we are well aware that the phenotypes and the genotypes are not linearly related. So we go for a non-linear approach also, so we can capture some total genetic effect. Our model reproducible kernel helper spice. So here I'm going to use two terminology basically. At the additive generic GBLUP model, we will give some estimated breeding value because we are using the genomic information, the genomic estimated breeding value. And but when we're using the outstanding GBLUP model, we are going to predict the variety performance, the clonal performance, which included additive and the total non-additive genetic effects. So this is basically the core of the GBLUP model, where we will use the genetic relationship between each clone. If you will see in this is a genetic relationship matrix of 2,909 elite clone. Here, each dot presented basically a genetic similarity between the clones. If you will see the white clone here, they are represented with more closely related clone than the pink clone. And in the standard GBLUP, we use exactly the same matrix, which can define our dominance covariance and epistatic relationship. So by statistical, what we did here, I would like to say thank you to SRA because they provide some initial data. Because our genomic prediction we did in a two-stage analysis. For the first stage analysis, SRA did some initial analysis, and that data we use as a phenotype in our prediction model. Where we series, reason, trials, we just considered as all of the fixed effect in our model, except the clone, we treat it as a random. And as well as we fit our model by including the heterozygosity, as we say. So in the clone, we just fix all the additive, dominance, and epistatic as a random effect. And then we extend our model by including the heterozygosity as a covariate. And the prediction accuracy, what we are saying, we are calculating as a correlation between the estimated breeding value or the predictive clonal performance with the observed phenotypic value. So I will show some results here proportion how the genetic variance will change. So if you will see here in the TCH, I will just say first, this letter represent additive model, which is basically GBLUP, classic GBLUP model. And AH mean I include heterozygosity in our model. In the third A, additive, and D, dominance, we include dominance in our model, and then it's complemented by the heterozygosity in the next model. And then in the we use additive, dominance, and E represent epistatic effects in our model. And this is the last is our full model, where we incorporate all the additive and non-additive effects with the heterozygosity. If you will see the TCH, if we will just use the GBLUP model, the additive variance is quite high. And when we will use the dominance in our model, if you will see the additive variance drop down significantly. And this green portion here, it's showing its dominance variance. And by including the epistatic in the model, the dominance variance get decreased. And we are amazed to see the most of the genetic variation in the TCH comes from the epistatic but I will say here, this is second order additive interaction effect. And if you will see, the residual constant remain constant in whatever the model we use it. As compared to TCS, if we will look at the CCS, when we will use the dominance in our model, there is not much affected. That means dominance is not really affect the sugar content. But when we will use the heterozygosity, the epistatic in the model, we can say the dominance is almost it's just gone, it's negligible, and some of the variation which comes from additive is due to some additive interaction effects. As we know, the fiber is the highest heritable trait, so this is more additive variance we can find in the fiber, and there is a less dominant effect in the fiber, but we can find some additive interaction in the fiber also. In all the trade, whatever we are using, all the models show the error variance quite keep constant. And if we this is also some literature are saying that some people are assuming also that if we will not fit any non-additive genetic effects in the model, this dominance and additive will count in a residual value. But in our study, we found that these are basically, I will say, our additive dominance and these are not orthogonal. They are because additive variance going continuously significantly down in this TCH. It might be one of the reasons because due to a low effective size, there's a high level of LD in the TCH. And if we go with a different prediction scenario to test some like training population size and yearly interaction, but I will just show you here some scenario one. If we will talk about the average prediction accuracy, if you will see the TCH, when we will use the additive model, and when we will extend our model, the full model, where we include dominance, apostatic, and heterozygosity, our prediction accuracy significantly improve in the TCH. Or we can say because TCH, the cane yield, is highly affected by the non-additive genetic variants, so it increased the prediction accuracy.
Seema, sorry to interrupt you. I think we've lost your share.
I'm sorry?
I'm no longer seeing your presentation. I'm not sure if anyone else is or if we've lost the screen share.
Oh, I'm not sure. So what do you want?
I can't see it either.
Okay. Can you share your screen again?
Okay. Right.
It just disappeared just a moment ago. So.
Oh really? I just share screen again. Right. Can you see my screen now?
It's coming back now. I'm wondering, maybe a couple of people, if you can make sure everyone's on mute, that might help a little bit just with the bandwidth. No, it's back now, so that's great. Thank you.
Oh, you can see, right?
Yes.
Okay.
Can you put it onto presentation mode again? Yep. Great, thank you.
Yeah. So if we will say the prediction accuracy, whatever the scenario we were talking about here, the cane yield, when we will extend our model, additive model to the final model where we include the non-additive and heterozygosity effect, our prediction accuracy significantly improve in the TCH. And we can say because the cane yield is highly affected by non-additive genetic effect, so by including non-additive effect in our model, significantly improve our prediction accuracy. And whereas the CCS and the fiber, the prediction accuracy is highest one in the our additive with the non-additive effect model, but they are not significantly affected. And then the fiber, I will say, is a higher heritability trait, so there was a no effect by including dominance and apostatic in the model. And the highest accuracy was when we put with the heterozygosity model, but there was no significant difference in the additive and the additive with the heterozygosity. So additive, so I will say the additive model will predict effectively in the fiber. And the same scenario we will found in the second scenario. So we will just say here by cane yield, which is highly affected by the non-additive genetic effect, the prediction accuracy is significantly improved rather than cane, sugar, and the fiber. And if we will look at the prediction accuracy based on the reason why, so regardless of the reason, I will say, here I'm talking about the scenario 2 where I will train my model with 2013 to 2016 and I predict the clones of 2017. So regardless of the reason, whatever model we use it, the full model where we use additive and non-additive effects, they predict well. They predict better as compared to all other models in the TCH. In the TCH, we found somehow the northern region with the lowest accuracy. And the highest accuracy was found in the Burdekin region, and where the accuracy was almost like a 0.5. So it's and we are amazed to see like there are some regions in Queensland where we can predict almost 50% that these are untested phenotype, and we can predict very accurately. So that's a good bet. And the CCS, if we will say somehow we can see the northern and southern region, they predict well, the prediction accuracy going high, but there was no significant effect whatever model we use it. In the central region, the accuracy of was lowest in the CCS. And when we will talk about the fiber, the central region again the less accuracy, and here there was no significant effect at what we use the model, but I will say the additive model was quite enough to predict the breeding values and the clonal performance in sugarcane in fiber. So I will summarize my work here. So genomic selection can increase the efficiency and accelerate the selection process in breeding program because we can early testing as soon as we have a DNA marker available, so we can reduce the cost of phenotyping. And as we see, we can predict complex trait more accurately when we incorporate the non-additive genetic effect into the genomic prediction model. And the most important, genomic selection we say is a potential. So we not only we will select some new crossing parents, but we can also identify the best clones for the varietal development. And this will give us a guide for us to choosing the mating pair in the next breeding cycle. And this is our my new objective I'm currently working on. I hope we will show our results soon. But the genomic selection, the implementation is quite still challenging, because the bigger question we also get, like, how can we use this breeding tool in the existing breeder scheme? So do we need to redesign our breeding program? So we just genotype clone at the seedling stage and just directly plant them on the final assessment trial? And the biggest question we need to how can we make available the improved variety to produce faster and improve the genetic gain in sugarcane? And sometimes the empirical evaluation is quite difficult due to long breeding cycle. So our group is also simulating the different breeding schemes, so we can optimize the genomic selection in sugarcane. So there are some, I will say, the future research, because in this study, what we use as a deployed model, because sugarcane is a highly polyploidy, and we didn't account any allelic doses in this study. So this is our future. We are going to use allelic information, allelic doses to creating our genomic relationship matrix. And the biggest challenge in sugarcane breeding program is the cost of SNP. And so we are the research should be going on the if we can able to develop some cheaper SNP, so we can implement genomic selection, because we can genotype. If we will genotype more, we can increase the selection intensity. That's automatically hands the generic cane. So I would like to thank first my supervising team, Professor Van Hees and Dr. Kai Wells, and my colleagues from the COFFEE and my review committee, Professor Mark Cooper and Katie Connor, from the SRA Special Science Forum, giving this funding and support of our work. Dr. Shinmin B give support every time that I need. Rabira Felicity Atkin, Emily Dillman, and from the CSIRO, I would like to say thanks, Karen, for the fruitful discussion. And I would like to say in the last, but the most important, the sugarcane grower for all their hard work and association basically with us. Thank you.
Thanks very much, Seema. Now, Stephen, I don't know, are you going to manage the question and answer session, or would you like me to do that?
I can.
All right.
I see there's no questions in the chat box. Does anyone have any questions they'd like to ask? So Phil Jackson has just posted a question.
I can see in chat box, one is the Phil question, and he is saying that by incorporating non-additive variants are only slightly increasing accuracy in cane yield from 0.28 to 0.32, but I think the percent heritability is around 0.7. So it seems there must be still large component of genetic variants that the model are not accounting for. Is this interpretation correct? The main limitation I would like to say here, because this is I'm sorry, is it? Can you hear me?
Yes, Seema. Yeah, you're right. You keep going. Yeah. Thank you.
Okay. Phil, what I'm thinking here, because we are using the diploid model, that's it's in a very high complex polyploidy crop. It's just a kind, give it just an approximation, and I will say, what we did basically in our model, it's just a statistical partition. It's not related to any biological additive and non-additive genetic effect. And I'm pretty sure about that. If we are going to use some allelic causes information, so we can get some more informable or more knowledgeable marker data we have. And hopefully we can increase our prediction accuracy by including these allelic causes. I hope this helps. The unmodeled variation might be.
This is Ben Hayes here. Can I add a point to Seema's great answer?
Yep.
Please do.
Is that okay, Alison?
Oh, definitely. Definitely.
The other thing is with non-additive and epistatic effects, we now know they're there, but we know from other species that to estimate these non-additive effects, you just need more and more data, so to estimate them accurately. So we still need to increase our reference set size, and that will help with our predictions of these non-additive effects.
Thank you, Ben. I noticed that I was just going to ask, actually, Philip, did you have anything else that you would like to ask? And I noticed that Jason's also added something. So just if anyone would like to continue with that question.
No, nothing more to add here. I look forward to having more discussions about it. It's interesting.
Mark Hetherington, I noticed that your microphone was on. A little moment ago, did you have a question that you wanted to ask?
Mark?
No? All good?
I can see one more question that Jason asked. The values of 0.28 and 0.32 are from a combined analysis, and the regional differences are significant. What I show the prediction accuracy is the average prediction accuracy across all the regions. Yes, there are a significant difference, we will say, we feel in the region wise. And I can see here, if we will specifically see the Burdekin, the sample size of the clone or the number of clones with growing the Burdekin are quite high as compared to central regions and the northern, I think. But I'm really exactly not sure that why there is such differences across the regions. But you got it right that these values, what you write before here, it's for our average prediction accuracy across the regions. And the Kevin asked, I may miss this, but why do you think the prediction accuracy level, the center was lower? Kevin, I really, I just got this basically that the prediction accuracy, we just find its center was lower. But I can say in the central, I think there was the sample size was the lowest in the central region. If this is a reason, I don't know if Professor Ben Hales want to give this answer.
Yes, I think Seema's quite right that it just depends on the size of the reference that you have in the particular regions. And for the Burdekin, we just have more clones with fat trials and fat data. So we're better able to predict the Burdekin.
Yes, yeah.
It does say there is a bit of a difference between the regions because the data from the Burdekin doesn't help us completely predict the northern region clones, for example, or the central region clones. So it is picking up differences between regions.
The Jason is asking one more question that, so I think, comment something. One more possibility could be the lower accuracy for TCH in central, the lower correlations between trial site and season. It might be very, I'm saying it might be, I'm agree that it can be one possible reason that the lower correlation between trial sites and the season. But I'm not 100% sure about this.
But yes, that would definitely reduce the accuracy for a region if it was less consistent between the years, because it means the information doesn't transfer as well across the years. For example, for the Burdekin, if it's very consistent how clones perform across years, that helps you have a better reference by combining the years.
I have one question, Seema, about the heterozygosity.
Yes.
Has genomic selection been implemented in any other polyploid crops? And how difficult was it to incorporate the heterozygosity aspect?
Actually, what we did, we used the genomic information to calculate our heterozygosity. I would say, because I use first, like I just told you, like additive information, but use the GRM, and the same I use the dominance relationship matrix among clones by using the SNP markers because we have a high density markers available, and by fitting in a model, it was really not hard because we just fit as a fixed effect. And the main reasons for including the heterozygosity, because when we use the dominance relationship matrix, basically what we did, we always overestimated the dominance value. And to get the right effect, so we had to, corrected the heterozygosity effect before in the model. And if you will see in my tables, my figure, when we will use the heterozygosity in our model, the dominance effect reduce. So for difficulty point of view, setting model, if we have a dominance relationship matrix is ready, which is a complicated to estimate first by computationally. But if your dominance relationship matrix is ready, so like say calculating inbreeding, heterozygosity is okay because we use the that matrix.
Yeah. So just to answer the other part of your question, genomic selection's been implemented in potato and Atlantic salmon, both of which are tetraploid.
Okay.
And they actually started out the same way we have, which is to treat it as a diploid, ignore the polyploidy, which is obviously wrong, but is a place to start and seems to work at some level. But in both potato and Atlantic salmon, they're now fitting these full tetraploid models, which take account of allele dosage, and they get some improvement from doing that.
Okay.
So it's certainly worth looking at in sugarcane.
Okay, thanks. Are there any more questions?
Got some great background noise. Doesn't look like we're getting any more questions coming through on the chat or people asking their questions. So if that's the case, we might wrap it up there. So thanks very much for attending. It's been great to see, you know, such a large number of people and the questions coming through. So there's obviously been quite a lot of interest. So we hope you found it value. Thanks very much, Seema, and to all of the Ben and Kai for participating as well. If you've got any feedback on the webinar, email it to me. My contact details are included in the event listing that's on our website, and it's actually in subsequent. My details are also in the information around our upcoming webinars as well. So when this one is removed from our website, the others will still be there. And just on that, our next webinar is scheduled for the 17th of February. And the topic is machine cane interactions. What is the impact of front-end design and harvester operation on product quality and crop retuning? And then we've got some other webinars scheduled for March and April. So check our website for details and keep an eye out for the email invitations. If you're not receiving those email notifications of our webinars and you'd like to, please get in contact with me and I can make sure that your details are added. So thanks once again for joining us, and I'll be putting the webinar up on our website if you would like to review any of the information. And have a great day, everyone.